EPR spectra of different copper complexes. For example, A is the EPR spectra of tetragonally elongated complex, and B is the tetragonally compressed copper complex, and this is orthorhombic complex, low symmetry copper complex, and this is exchange coupled copper complex. Let us now see these. For example, in the case of copper, I equal to 3 by 2. So there will be 4 lines. I equal to 3 by 2, 2 into 3 by 4 lines, as you see here. 1, 2, 3, 4. This is G parallel. For example, this is G parallel. This direction is G parallel, and this direction and these two directions are G perpendicular. Therefore, there are two G perpendiculars. The signal is more intense, whereas the hyperfine coupling, because the electron, the unpaired electron present in copper couples with the copper nucleus to give 4 lines. This is the hyperfine coupling constant. In this case, in G perpendicular, it is not resolved. Here in copper complex is JT active, it is undergoing strong John-Taylor distortion. Therefore, and the axial ligands are elongated, axial bonds are elongated, the equatorial bonds are compressed, and G parallel value is greater than, if G parallel value is greater than G perpendicular, then it is tetragonally elongated copper complex. There are certain conditions in the crystal constraint, lattice constraint. There are also copper complexes in JT compressed state. In this case, G perpendicular is greater than G parallel. If G perpendicular is greater than G parallel, then it is tetragonally compressed complex. In the case of orthorhombic less symmetric complex, G1, G2, G3, they are not equal. G1 not equal to G2, G2 not equal to G3. And in the case of pure copper complex, there will be exchange interaction between the neighboring copper ion to give exchange coupled narrowed single line. We don't get 4 lines. It is expected to give 4 lines, but due to exchange coupling, we only get single line as shown here. EPR spectra of vanadyl ion, it is a D1 species. The I value for vanadium is 7 by 2. Therefore, the unpaired electron couples with the vanadium nucleus to give 8 lines. The solution EPR of vanadyl EPR at room temperature, it gives 8 lines as shown here. At low temperature, the same solution at low temperature, it gives it is also tetragonal complex. Therefore, you will be getting G parallel, G perpendicular. You see G parallel, G perpendicular, similar to copper complex, and A parallel, A perpendicular. For powder, low temperature EPR of in the powder, all the orientations are possible. So you will get magnetic field perpendicular to the tetragonal elongation axis or x-axis, y-axis perpendicular. So you will get G parallel, G perpendicular. In case of solution EPR, it is isotropic because of tumbling motion. The spectrum obtained is isotropic, whereas the spectrum obtained in the case of powder EPR at low temperature or solution at low temperature, it gives anisotropic because of the orientation of the molecules at low temperature. In Medical College of Wisconsin, I have studied the thiol oxidase activity, peroxidase activity using pulse EPR, NMR, ENDOR, etc. We have studied the changes in the structure of the active site